Alrighty, welcome back in, everybody, to a brand new chapter dealing extensively with right triangles. Really important chapter, especially for those who want to move on to pre-calculus. The topic today is similarity in right triangles. This is going to get a little bit difficult, but I'll try to walk you through it and see if we can get it. So basically, this revolves around a theorem that when you draw the altitude to the hypotenuse of a right triangle, which you see here in red, that's an altitude drawn to the hypotenuse of a right triangle. So your right triangle is BCA, and you're drawing an altitude to its hypotenuse, which is CD here. What you do is you divide that right triangle into two smaller triangles, and all three of the triangles are actually similar to each other, both the two inside triangles and the outside triangles. And the reason why they're similar, I'll just kind of talk you through that. Let's take the outside triangle ABC and prove it similar to this small one right here that I'm pointing at. So each of those triangles here have a right angle, right angle for each of the two triangles, and they both share angle B. So the outside triangle and the little triangle inside are similar by angle similarity. Likewise, if you compare the outside triangle with the larger of the two inside triangles, again, they're both right triangles. They both have a right angle, and they share angle A. So they're also similar by angle similarity. So since the outside triangle is similar to the smaller inside and to the larger inside triangles, those two inside triangles are also similar to each other. So all three triangles are similar. So we can write a similarity statement relating all three triangles to each other. So I'm going to refer to the outside triangle, the smaller inside, and the larger inside as I talk through this. So triangle BCA is the outside triangle. So you see it right there, triangle BCA. That's going to be similar to triangle BDC, which is the small inside. So BDC. Okay. And then that's also similar to the large triangle here, CDA, the large inside triangle, CDA. Right there. So that's the letters that you're going to use there to write that correspondence. Okay, so we're going to get some more practice with that. Again, we have the same situation. We have a right triangle JKL, and you draw the altitude to the hypotenuse of that right triangle. That altitude is JM. And then when you do that, you form three similar triangles. So they're wanting us to write that similarity statement. So again, I'll refer to the outside triangle, the large inside, and the small inside. So the large outside triangle, JLK. So JLK, you can see that one. It's going to be similar to the large inside, which is MJK, and also similar to the small inside, MLJ. So that these letters should correspond correctly for those three similar triangles. Okay, before we get into our last two theorems, which are really what we're heading toward, we have to do some vocabulary here. Geometric means. So if you write the proportion A over X equals X over B right here, remember that these two positions here are called the means. And if we put the same variable or the same number in both those positions where the means go, we would say that X, or that position, that whatever number that is, X is a geometric mean between A and B, the other two numbers on the extremes. Okay, so just a little vocabulary. So we can use that then to solve a couple example problems with that. So if it says find the geometric mean between 4 and 9, I'm going to set up an empty proportion, and 4 and 9 are going to be put in the extremes part. And the geometric mean is what we're looking for. Remember, that's these two spots right here. Geometric mean goes in both of the spots for the means. And then to find that geometric mean, you're just going to solve for X, so cross multiply. So X squared equals 36. And although X is really plus or minus 6, to solve that equation, we're just going to keep that plus. We're going to keep that positive square root for the geometric mean here. Okay, let's do that one more time. This time, let's find the geometric mean between 6 and 15. So again, we're going to write an empty proportion here. We're going to find the geometric mean. So we're going to find this number right here. Remember, it's the same in both spots. Find the geometric mean between 6 and 15. Okay, so there we go. Again, we just solve it by cross-multiplying like we normally do. So x squared is equal to 90. And then x equals, again, we're going to take that positive square root, not the negative one. So that geometric mean is the square root of 90. And of course, we want to simplify that radical like we've done in the past. So we're going to write that square root of 90 as a square root of 9 times the square root of 10, because 9 is a perfect square. And so we're going to end up with x equals 3 times the square root of 10, which is the geometric mean between 6 and 15. So 3 times the square root of 10. Okay, so that geometric mean idea is going to come in handy for our next two theorems. Okay, this part's going to be a little bit complicated, so you're going to need to watch closely. So you see the big triangle, the outside triangle BCA. We drew the altitude to its hypotenuse. So that altitude would be CD. And I guess maybe I didn't mention it, maybe you don't need to know, but that altitude is a perpendicular segment. So CD is the altitude to segment BA. So if we look at the two inside triangles, compare those, remember those are similar to each other, we can say y over h. So y is the longer leg of the larger of the two inside triangles, so that's going to correspond to h, the longer leg of the smaller triangle. So that ratio is equal to h over x. So h is a shorter leg of the bigger inside triangle, and that corresponds to the x, which is the shorter leg of the smaller inside triangle. So if you look at this proportion, notice that h actually is the geometric mean between y and x. H is the geometric mean between y and x. So if you zoom out a bit and look at now the big triangle, h was that altitude that we drew, and it's the geometric mean between these two parts of the hypotenuse, x and y. So I just proved our theorem here for you. I'm going to scroll down and read to you here. And that is the altitude to the hypotenuse of a right triangle is the geometric mean between the two segments of the hypotenuse. So again, saying that again and looking at this altitude h is the geometric mean between these two pieces of the hypotenuse that altitude was drawn to, so x and y. So h is the geometric mean between x and y there. So we're going to use that to solve problems here. Okay, so regarding the same exact picture here, I'm going to go through a couple proportions here, and then we'll look at that last theorem we're going to look at for today. So now compare this time. Remember, all three of these triangles are similar. Compare the outside triangle, that's the large one, BCA, with that small inside, so with this one. So C over A, if I look at that ratio, C is the hypotenuse of the large outside triangle. That corresponds to A, the hypotenuse of that small inside triangle. So that ratio is going to be equal to A over X. A is a smaller leg of the big outside triangle. That's going to be corresponding to X, which is a smaller leg of the small inside triangle. So C over A equals A over X because those are two pairs of corresponding sides. And again, look at this situation here where we have A is the geometric mean between C and X. Okay, now zoom out again and look at the big triangle, the big outside triangle. A is one of its legs, and so it is the geometric mean between the hypotenuse and the part of that hypotenuse touching that leg. So A, this leg, is a geometric mean between C and X. And that's what that proportion says. And that's what our other theorem says. So I'll read you that theorem, and then we'll do that last proportion. So the other theorem that we're going to need today is each leg of a right triangle is the geometric mean of the hypotenuse and the piece of the hypotenuse touching that leg. So let's see if that theorem holds again for the other leg of that right triangle. So this time we're looking at the outside triangle, BCA, And we know that it's similar to that greater of the two inside triangles, larger inside triangle. So we can set up our proportion. So C over B, that's the hypotenuse of the outside triangle, is going to correspond to B, which is the hypotenuse of the larger inside triangle. They're both hypotenuse, so that's a ratio. And B, which is the longer leg of the outside triangle, corresponds to Y, which is the longer leg of that large inside triangle. So that's another proportion that's true because of the two similar triangles. So if you look at that closer, you'll see that B right here is the geometric mean between C and Y. Now let's zoom out again and look at our diagram. So B, this leg of the original outside triangle, is the geometric mean between the hypotenuse, its own hypotenuse, and the part of the hypotenuse touching that leg, which is the Y. So again, that's what that theorem says. I'll read it again. Each leg of a right triangle is the geometric mean of the hypotenuse and the piece of that hypotenuse touching that leg. So that's a lot to think about. So let's go ahead and apply that to our last example here, and then we'll get some practice problems. Okay, so you see here the situation that we have. It's not as complicated here. You got a right triangle, the big one, and we've drawn the altitude to its hypotenuse, which is x. And so our first of our theorems here said that altitude is the geometric mean between the two pieces of the hypotenuse. So we're going to set up an empty proportion like we're used to doing, and we're going to fill in that geometric mean first. So that altitude is the geometric mean, so it goes in those two spots between the two pieces of that hypotenuse there, the 10 and the 2. So those go in the other two spots. Okay, so we're going to find that altitude. So that's going to be x squared is equal to 20 using the cross products. And again, x equals the square root of 20. Again, just the positive square root we want. And then we'll simplify that radical. So we know that that's x equals the square root of 4 times the square root of 5. And so we're going to go ahead and simplify that and say that x equals 2 times the square root of 5. Okay, so we actually just calculated the altitude of that triangle there. Okay, now we're going to find y and z. So that's a different theorem. I get an empty proportion. This is that theorem that said that each leg of a right triangle is, after you draw that altitude, of course, to the hypotenuse of the right triangle, each leg is a geometric mean between that hypotenuse, I should say, and the piece of that hypotenuse touching that leg. So when you see that, put in, if you're looking for y there, you're looking for that leg, that's the geometric mean. So we're going to put that in the two spots where the geometric means go. And so then recall the theorem, that leg, remember the original right triangle, is a geometric mean between the hypotenuse, which is the 10 plus 2, right? That's the 12. That's the entire hypotenuse there of the big triangle, big outside triangle, and the part of that hypotenuse touching that leg, which is the 10. So we got y squared is equal to 120. So y is equal to the square root of 120. And we got to simplify that. Okay, so how are we going to do that? Y equals, well, let's see. Got to find two numbers to multiply to give 120, one of which is a perfect square. And I can think of 4, but I wonder if there's a bigger one than that. Well, I'll start with 4 because I can't think of anything bigger right now. So 4 times 30 is 120. So we got 2 times the square root of 30. And that's going to be it. Yeah, I guess we got that simplified right away. So that's going to be that y we just calculated. We just calculated this leg of that original right triangle. Okay, the last thing we're going to calculate is the z, the other leg of the original right triangle. And then we've solved this problem. So let's set up an empty proportion. So this time that leg z is a geometric mean. So we're going to write that in first. Again, the same thing. Recall the same theorem. That leg of the original right triangle, after you draw that altitude to the hypotenuse, is that z, that leg, is a geometric mean between the hypotenuse, which is the 10 plus 2 is 12, and the part of that hypotenuse touching that leg. So this time the 2 is touching that leg. So z, that leg, is a geometric mean between 12 and 2. So we'll go ahead and solve that proportion. So z squared is equal to 24. Z is going to be that positive square root of 24. And so we're going to write that as z equals the square root of 4 times the square root of 6. So z equals 2 times the square root of 6. All right, so we were able to, with our new theorems, once we know that we've drawn the altitude to the hypotenuse of a right triangle, to kind of recap what we're doing here, when you draw that altitude, you divide that right triangle into two other right triangles, which are similar to each other and to the original. So you got three similar triangles altogether. So that's the main point. But then we had kind of two corollaries that followed from that, which is that altitude itself that you just drew is the geometric mean between the two pieces of the hypotenuse. The two pieces of the hypotenuse. They're the geometric mean, remember, being these numbers and these positions here, which we call the means, the same number in both positions. So that altitude is a geometric mean between the two pieces of the hypotenuse. And then the other corollary was that each leg, so remember it has two legs, each leg is a geometric mean between the entire hypotenuse and the part of that hypotenuse touching that leg. So we can apply that really twice because the right triangle has two legs. So same thing over with this leg. This leg is a geometric mean between the entire hypotenuse and the part of that hypotenuse touching that leg. Okay, so this is definitely one of the theorems and topics that we need to get some practice on. And I think once you set up a few and get the hang of it, you're going to be okay with this. But it's going to take some practice. So we got a couple versions to work on for this. And so let's go ahead and give that a try. All right, good luck.